And here is some eddy current information. And as you can expect, you have a high density of the current on the outside of the sleeve and maybe not so much in the middle. Okay? So here is what we get for, and we did the two just to verify that if we do only one, we actually capture the right stuff, and we can see it's about the same stuff. So for one sleeve, we get about half a watt, a little less than a watt. So and this actually builds the machine. They're actually trying to build the machine now, and we're going to see how this all stacks up. But it could be quite interesting. Last example. This is an example of an actual machine. You can find them on wind generator, you can find them windmill generators, you can find them in when you have in-wheel type of things. This machine is essentially two rotor, and again the geometry is a little changed. It's not really the way it is, but it doesn't matter. It's a high pole machine. You have two rotors, and you have in the middle of the air gap a layer of conductors. And the idea here is that those conductors are formed. So they're big conductors, they hold by themselves, because you don't have to, in this case, have specific stuff to hold them back. The idea is very good, but look at this. You have absolutely no shielding of the conductor, which means that the conductor are going to cut exactly all of the flux. In a traditional machine, you have teeth, and those teeth kind of guide the flux around the conductor. The conductor never sees the field. But here, no way. It has to cut the field. And sure enough, so let's look at a few computations. Here is this two rotor, air gap winding, three-phase 60 pole, let's say the high point. Average radius 140 millimeters, neodymiums, cup coils. And so the computation we did was just, okay, that's the winding. You have the three phases, and actually it's you have the three phases, and it actually goes, it switches around and stuff like this. Keep in mind here so that you have a winding on the outside, a winding on the outside, and one in the middle of the two. So they're not going to see exactly the same thing. This is the mesh, 3D mesh. Let me point to you the type of mesh we're using here. We have extruded mesh, quite in a few places. That means that it takes the mesh in the space and extrudes it vertically. Of course, the mesh inside the copper parts need to take care of the eddy current. This is the flux map, so I'm rotating this at constant speed. This is the flux map. And I'm going to do this at 500 RPM, 1070 to 2500, 5000, 7500. And if I remember very well, I think this machine was rated for 8000 RPM. This is a motor, it's not a generator, it's a motor. So it's supposed to produce some motion. Sadly, it doesn't produce very much motion. Here are the eddy current distribution at 5000 RPM. So remember I told you this is just going across a pole. So you can see right there the effect of the flux density going through it. Losses over 360 electrical degrees, and at 5000 RPM, it's the peak is 396 watt. This is the detail of the current, and here you can see very well that the stuff which is out of the air gap doesn't see anything. But everything which is inside the air gap, you can see the circulation of eddy current, which is quite big actually. Here are the losses at 5000 RPM for the three phases. So here is one phase, this is the one in the middle, and this is the one on the outside. The difference, you would expect to have the same one, but you cannot have the same one because the middle layers is shielded by the two layers on both sides. Okay? So if I add all of those, I get 300 watts for the coils. And if I look and multiply this for the whole machine, I get 5 kilowatt basically. And so that's not very good because the machine is actually done for, I think, somewhere around 10 kilowatts. So that would give us half of the power that goes down to the coils. Okay?